Hello, here in this video we're going to go over the Chapter 5 review. I have the answer key up here for us so that I can just go through and highlight the different concepts of each different types of problem. If I was to do this from scratch, it would take, much longer. Now, for us here, this first section, 1 through 4, is just simplifying square roots, cube roots, depending on what the index is. And remember the way that this works, for the square root is that we'll square root to 121. And then for the y to the 10th power, remember we're essentially just dividing by whatever the index is. So 10 divided by 2 gives us that y to the 5th power there. Similarly for number 2, the cube root of 8 is 2. This time our index is the 3 for the cube root, so g to the 6th power underneath the cube root would be g squared. This one here, just a little bit of a change up in terms of a type of problem. These are two things multiplying by each other, just like on the previous one, the 8 and the g to the 6th power, two things multiplying together. So in this one, we'll take the square root, and then something to the 4th power underneath the square root would come out squared. Number 4 is just reminding us that we can divide first and then take the cube root, or just cube root right from the beginning, depending on whichever your preference is, and that's the answer that we would get. All right. So, and as you can see, some of the numbers jump around here as I kind of deleted some off this review. The temperature T in degrees Celsius of a liquid T minutes after heating is given by this formula. When is the temperature 48 degrees Celsius? So this is one to where we could have found the inverse of this formula if we wanted. We could also just pay attention and recognize that the 48 degrees is what we need to plug in for the capital T and then solve for T manually. We also would have gotten this same answer if we would have found the inverse of this function to where we could then isolate the time. But either one of those methods would work. So here's some more properties of radicals to where, on number 9, you can multiply the inside components first and then do the cube root. And then you can see the different, work shown on those as we go through and break down the different components. For adding and subtracting, remember that two things must be true in order to add and subtract radicals. They have to have the same radicand, so the stuff underneath the radical sign, and the same index. Number 17, for example, the square root of 2 and square root of 3 are not the same radicand, so those can't go together. But then once you do have the same radicands, all you're doing is simply combining the coefficients out front with addition or subtraction. So on 18, we just did 1 minus 2 to get that negative 1. The radicands don't change. On 19 and 20, it's a reminder that we can simplify first, right, to where this one, 32 16 times 2, square root that 16 to get the 4, 3 times 4 is the 12. And then by the time we get all those simplified for both 19 and 20, we are adding the coefficients to determine how many of the different radicands that we have. If we're level 3, I had us multiplying complex conjugates, which is where you'll have the same A and B. So if you look in both of these parenthesis groups, the term on the left and the term on the right are the same. So on this one, both these are 1 and a square root of 3, 1 and a square root of 3. But one will be positive and one will be negative. And when we do that, you can see I highlighted here with colors. The yellow highlight paths always cancel out because of that plus minus symmetry. So these end up just becoming regular old whole numbers. And you'll use complex conjugates in calculus to help clear some denominators when you have square roots and things in the denominators. 25 through 32, these types of questions here, which are the more complicated type of exponential problems, won't be expressed on the test, but these do help you demonstrate a strong mastery over exponents in the concepts of if you have something to the 1 over n power, That's the same thing as the nth root of that concept. So definitely check these out because they allow you to demonstrate full-on exponent mastery, but these types of questions won't be present for us on the test. In the 5.6 section, this is where we're going through and solving our radical equations, which involves getting the square root term isolated, which on these first three here, 33, 34, and 35, they are already isolated. You get the square root term isolated, and then you square both sides. Now, sometimes it's easy, like on 34, when I square both sides. On 33, when I square both sides, it ends up making the right-hand side a quadratic, which you can then see me get it set up equal to 0, so that we can solve that quadratic. And when you go through the whole process of these, and you find your answers at the end, you'll see me checking the answers and crossing some of them off. For 33, when I plug 0 back into the original equation, you'll see that it ends up not working. Meanwhile, the 3 does. 0 is what we call an extraneous solution. So we'd be expected to list it, but then it doesn't check out in the original equation, so we mark it off. And that's what happens on 34 as well. And that happens for a variety of situations. One of the reasons it happens on 34 is if you look back at the original equation, it's a square root is equal to a negative number, which we know we can't have that happen unless we're using imaginary solutions. So up here for 36 and 38, same concepts. What makes 38 tricky though is that we can't isolate all the square roots at the same time. So we instead have to, I isolated the square root of x plus 9 first, squared both sides, which turned the right-hand side into, square root of x plus 1 times another square root of x plus 1. And then I continued on through the process of getting it isolated. And then once I got the other square root, the final square root isolated in this step here, and I squared both sides, we get the answer is equal to 16. And you can plug that into the original equation and double check that it does indeed work. For 5.1, this is operations on functions. So what we have to do here is just follow what they ask. For 39, they want us to do f plus g of x. So I literally just take function f and I add it with function g. And when I do that and gather up like terms, that's what we get. For 40, when you go to subtract g of x, do be sure to remember that you have to distribute that subtraction sign to both. Same thing for 41. We'll distribute that subtraction sign to both because we're subtracting all of function f, not just, a single piece of it. Down here on 43 and 44, this is a reminder that whenever we end up creating a fraction by doing division with operations of functions, that we do need to check for values that can make the denominator 0. So on 44, you'll see that I set the denominator up equal to 0 and solved, and found that if x is equal to 1/4, it makes the denominator 0, which would cause an error. So we mentioned here for the domain that x cannot equal 1/4. Now for the denominator on 43, 2x squared plus 3 can never equal 0. And a quick version of why that is that would be a quadratic with a y-intercept of 3, and it would open up. And that never crosses over the x-axis, so 2x squared plus 3 is always positive. So there's no domain restrictions on 43. For this next set here, 5.2, this is composition of functions. This is different than 5.1. In 5.2, this is where the order matters. We have to do one of these first, and then we take that answer and continue forward. So on 45, f of j of 3, and you can see I highlighted j of 3, means I need to find j of 3 first. So all I'm doing here first is finding j of 3. Once I found that j of 3 is equal to 2, if j of 3 is equal to 2, you'll notice that we're solving now for f of 2. So on composition of functions, you need to find that inside piece first. We talked about it as a Thanksgiving turkey, to where this is turkey f of x. We need to figure out what kind of stuffing we have first. So we found out j of 3, which told us the type of stuffing, and then we put that stuffing into turkey f to finish finding the answer. So you'll notice that that's happening here on each and every one of these composition of functions. I find that highlighted portion first, and then I go through, plug in that answer back into the turkey, if you will. All right, so always find that inside one first. All you're doing on this is doing, function notation twice. So like on 46, we found h of -1. We found that that answer was 7. So then I took the 7 back up and used it with j, and did j of 7. For 48, we're not expecting a numerical answer because what we had to plug in to f was a. So I went into function f and replaced everywhere I had an x with an a. When I did that, it gave me -3a plus 2. So I plugged that into g, and then I went to g, and everywhere that I had an x, which you can see was just in the numerator of the fraction, I replaced it with -3a plus 2. Okay. So for 5.3, that was us finding the inverse. And the first step on finding the inverse was you swap the two variables, so you switch x and y, and then you resolve. So you can see here, like on 51, y became x became y. I resolved. Now notice that we do not want the plus or minus symbol. Don't put those there. We're only considering the positive arm of this. Because when we find the inverse of a quadratic, it turns sideways, but that's no longer a function unless we don't include the negative portion. So for 53, when we're working with actual formulas, it's like this is the area of a circle. To find an inverse, you don't swap the variables out because it wouldn't make any sense exchanging area for radius because they're different things. So instead, when you're working with an already pre-established formula, what it means to find the inverse is just to solve for the other variable. So initially, area is equal to pi r squared. Area is what's isolated. And so we needed to go through and solve it for the radius. And so I didn't do any variable swapping. I just started right away trying to solve for the radius. And then we get that the radius is equal to the square root of the area divided by pi. And then we plugged in the area of 82 inches squared, divided it by pi, and took the square root. And that would tell us what the radius for that circle would be. Okay. Now, here for us on the test, the graphs are already going to be made for you, and we'll just make discussions off of the graphs. But the way to do these situations here for 54, 55, and 56, you'll see in teal I made the parent function of y is equal to the square root of x. All right, and what that came from is, if you just make this table, we did it back on the notes, we picked different numbers that square rooted easily. All right, and so I just plotted those numbers to where I take the square root of those different x coordinates to find my y values. And then we apply the shifts. So like on 54, that tells us it's a horizontal shift to the left 3, because horizontal shifts are always opposite of what you'd expect. 55, that subtract 1's on the outside, so that's a vertical shift. So all I did was took that teal graph of y is equal to the square root of x and shifted it down 1. For the domain and range, when you have the picture there, The domain, we talk about where the x values begin and then what direction they go. So for 54, for example, when we're looking at the red function, it got shifted to the left 3. So my domain would be anything when x is greater than or equal to -3, because I don't go anywhere to the left of that. And my range is y is greater than or equal to 0. Because if you look at that red graph, it never goes lower than 0 in the y direction. All right, so you can use the picture to help identify the domain and range. For 56 here, what we have to do first is here's the parent function. So that's step 1. Step 2 is you just double all the y values, right? I went from 3 to 6, went from 2 to 4, from 1 to 2. Then step 3 is we can apply the negative sign. So that just reflects it over the y-axis. And then the final step here for step 4 is that's when we would move it to the right 2. So you do have to do it in that order first. You don't want to move it to the right 2 and then double everything and then reflect it. You want to do the doubling and then the reflection. You can flip-flop those if you want, because they're both just a multiplication, but so make sure that you take care of that number on the outside first, which is the -2. So we doubled everything, reflected it, and then did the shift last. If you're not given a picture, remember the way to find the domain is you take it and you set it up greater than or equal to 0 and solve. Now the range always just starts at y is greater than or equal to 0, and whatever type of vertical shift we have, which in this case it was a 5, impacts the range. The only time that it can get a little confusing is when we do a reflection. Like on this last one here, this light purple was our answer. So now the range is y is less than or equal to 0, because that graph never goes higher than 0. All right. For the cube roots here, it says describe the transformations, list the inflection point, graph the ones requested. You may need to graph some points as decimals, estimations using the table on your calculator. So what I did to graph these was I typed them into the calculator, and you can do this from a parent function perspective as well, but a lot of times we'll just get these guys typed in and then go to, because it mentioned the table, we get to the table by pushing second graph. And if you're wondering, how do I get the cube root, because I know to push y equals, the button in the top left to start graphing. If you want to get the cube root symbol, that's the math button on the far left, and then it's option 4, which gives you the cube root. Now, the inflection point is very easy to identify. It naturally starts at 0, 0, and then the shifts apply their changes. So that is a shift of going to the right 2. That is a shift of going up 1. So when I apply those two things to 0, 0, it's no longer at 0, 0. It would now be at 2, 1. And for 59, the only shift that happens is a vertical shift up 1. So that's why my inflection point went from 0, 0 to up 1. For this one here, I had us go through and find that I gave us an original function, f of x is equal to x cubed minus 1, and I asked us to graph both it and its inverse on the same grid. So before I could find the inverse to type into my calculator, we needed to go through and locate that. So that's why right here, for the inverse, changed y to x, x to y, and I went through the process of solving by using cube roots. All right, and I found that the inverse function was the cube root of x plus 1. And when I graph both of those into my calculator at the same time and go to second table, you'll see that we get this set up here. And that shouldn't be a surprise because we know that whenever we are finding an inverse, it reflects the graph across the line y is equal to x, which should make sense because when we found an inverse, all we did was rotate the y and x's and resolve. So that's why when we graph it, it reflects across the line y is equal to x. For the level 3s, we did, this is an extension of 5.6, solving radical equations, where we had to do them as inequalities. The first step on solving these guys as inequalities was to go through and just solve it like normal. So isolate the square root and square both sides and solve for that inequality. But the second component that we had to do is we had to set the radicand. All right, so we had to set the radicand up, which is the values underneath the square root sign, greater than or equal to 0, because we're not allowed to have a negative number up underneath that square root sign. And then when we do that, we see a second inequality, and then we essentially find the intersection of where both of those things would be true. So for example, on this first one, when we solved initially, we saw here that x had to be greater than or equal to 8. But then when we set the radicand up greater than or equal to 0, we saw that x had to be greater than or equal to -1. And so when we factor those two things in together, if you need to be greater than or equal to -1 and you need to be greater than or equal to 8, those would both start once x is greater than 8. Because if x is greater than 8, I'm automatically greater than or equal to -1 as well. Sometimes though, like on this one here, we go through and solved it initially and saw that x needed to be less than 26. When I set the radicand up equal to be greater than or equal to 0, I get that x needs to be greater than or equal to -1. Now those two things, have a middle ground. So the only time that this inequality will work is when x is both greater than or equal to -1, but also less than 26. If I pick a number that's too large, like 28, it doesn't verify the initial solution. If I pick a number that's too small, like -10, it then makes my radical 0 or less than 0, which would make it less than 0, causing it to be a negative number, which means we can't have that either. So the only values for x that will work on this particular problem is the ones that satisfy both of those at the same time, which is when x is in between -1 and 26. And then a similar concept happens here on the last one as well. So hopefully this video helped maybe jog your memory a little bit on some of the different components or some of the trickier components. You can see here, even just doing a quick coverage, this video is almost 25 minutes. So this review definitely has some substance to it. So continue to work on it and double check your answers and making sure you're getting ready for the test.